So good afternoon. This is Richard Gemark, and I'm going to be serving as the moderator for today's webinar. So this webinar is put on by the Southwest CMG. We are a regional chapter of the CMG organization focused in mainly Texas. We try to have meetings at least 3 times a year, usually in the Dallas-Fort Worth area, Austin, San Antonio, and Houston. We are an official meetup group, and we'll give you a couple reminders during this webinar that we encourage you to join our meetup group, because that's where we're going to post information about the presentation materials, the recording that we get from today's webinar. So we're going to have 2 presentations today. Fred Moyer from Circonus talking about the problems with percentiles in aggregating data, and then we'll have Colette Downey from Caringo talking about object storage and an interesting performance benchmark that they ran. So moving on to the next slide. This is just a few words about CMG National Organization. They've been around since 1976 when it was pretty much mainframe only. But today they look at a variety of platforms. IoT, web, mobile, distributed, Windows, Unix, you name it, they have it. And these are people who are looking at the performance and capacity planning, performance engineering of both the infrastructure and the applications. So take a look at their website. They have some interesting stuff. And slide 3, this is just a reminder about the annual CMG conference coming up in about 2 weeks in Seattle. And there's still time to register. So let's get into the first presentation. So the first presenter will be Fred Moyer, a developer evangelist at Circonus. Now, Fred has an extensive background in software development, and he's using that expertise to find ways to better manage, analyze, and understand big data. And the one thing that I had to look up was this White Camel Award. So this is an award from Perl mongers that recognizes significant contributions to the Perl community. So questions, enter them in the chat window that you'll see on the right-hand side of your screen, and we'll answer them at the end. So now I'm going to turn this over to Fred Moyer.
Okay, hello folks. Can you hear me okay? Hey Richard, can you hear me?
Yes, I think we can.
Oh, great. Okay, I'll get started. Okay, hi folks, I'm Fred Moyer. Getting over a bit of a cold, so I sound a bit raspier than normal. So today I'll be talking about the problem with percentiles. I'm a developer evangelist at Circonus, which means I'm basically an engineer who talks to people. My Twitter handle is the bottom left, and that's Fred Moyer with a PH and 7F. I want to give a quick shout out to my colleague Heinrich Hartmann, who is a data scientist and originally did a blog post on the material I'm about to present. So let's go ahead and get started. So latency. Usually I ask how many people here think that latency is an important metric to track in their applications. And generally the answer is it's important for almost everybody, and commonly used as a business critical metric. If your application is not responding quickly, that's going to affect your customers and in turn going to affect you. So I'll pose another question. For any of your services, how many requests were served within 550 milliseconds over the last month? I don't expect people to know that off the top of your head, but how would you go about determining that with your existing systems? There's a lot of tools out there that can glean information from your systems, and you probably have a means of getting that data, but I would also like you to ask yourself, how accurate would your answer be? How accurate do you think it would be, and how accurate do you need it to be? Are you Not everyone is Google, who processes, billions of requests per second and needs to have, that kind of precision. But often it's good to be aware of, like, how accurate are the answers you're getting from your monitoring or your observability systems. So I'll go over the agenda today. I'm going to do a quick primer on service level objectives, and then go through a common mistake with percentiles. And then we'll talk about computing SLOs with log data, computing SLOs by counting requests, and computing SLOs with histograms. So service level objectives. A bunch of people here are probably familiar with the Google SRE book. That concept of SLAs has been around for 2 decades at least, but service level objectives and service level indicators are quickly becoming ubiquitous among site reliability engineers. The amount of online content around these terms have been increasing rapidly. So these 3 terms, SLI, SLO, and SLA, are now fairly standard lexicon amongst site reliability engineers. In addition to the Google SRE book, there's 2 other recent books that talk about service level objectives. The Site Reliability Workbook has a dedicated chapter on service level objectives, and Seeking SRE has a chapter on defining SLOs by Theo Schlossnagel, the Circonus CEO who got me into this stuff 5 or 6 years ago. One thing to note is that there isn't a standard definition of SLO. Everyone's business needs are different, and what you should take away from these books and their discussions of service level objectives is there are many ways to define them. So you should base your definition of a service level objective on one that makes the most sense for your business. Now, there's a YouTube video out there put on by Seth Vargo and Liz Fong Jones called SLOs, SLIs, SLOs, SLAs, oh my. And it is really good at defining these terms. The first part of the video speaks that SLIs drive SLOs, which informs SLAs. So service level indicator is basically a metric derived measure of health for a service. For example, I could have an SLI that says my 99th percentile of homepage requests over the last 5 minutes should be less than 300 milliseconds. A pretty common, indicator that folks are probably familiar with. And then we have service level objectives. We could say that an SLO is what we want to meet the criteria set by the SLI for 3 nines over a trailing year window. SLOs are basically SLAs, but relaxed. SLAs take SLOs one step further. They're generally crafted by lawyers to limit the possibility of having to give customers money for those times when our service doesn't perform like we are committed to. And, we can define SLAs based on SLOs, but the SLOs are generally quite a bit relaxed, as those are the internal targets that we want to hit for our service so that we're, protected from violating our own SLAs. So an example SLO would be 99th percentile homepage SLI will succeed 99.9% over the trailing year. So we've done a very quick SLO primer. There's lots more material out there, and these slides will be available so you can take a look at the video or, go grab a couple of those books and read through them. They're really excellent. So let's take a look at really the common mistake when using percentiles that I see happening quite often, often on a weekly or monthly basis on sites like Reddit or Hacker News. People talk about making this mistake with percentiles, and that mistake is averaging percentiles. So averaging percentiles is probably the single most common mistake when working with latency metrics. And why is that? Part of this happens because averaging percentiles is actually a reasonable approach when your systems are functioning normally and all your nodes are exhibiting symmetric workloads. It's easy to get an idea of aggregate system performance in these situations just by adding up percentiles from nodes and dividing by the number of nodes. And the data from most monitoring systems out there makes this very easy to do. When this approach becomes problematic, though, is when node workloads are asymmetric. If you're looking at an average of percentiles when that happens, You won't often know it though. This approach hides those asymmetries. So this is a graph of 5-minute P99, P95, P90, and P50 values over 24 hours. P99 value is the highest, P50 is the lowest. So I would ask you, what's the P99 over this entire time range, which is about, maybe about 24 hours. So if we examine the graph, we have a peak of about 300 microseconds latency for 6 hours for the P99, and it goes down to about 180 microseconds for the other 18 hours. So, we can approximate and take a guess and say the P99 is probably around 200 microseconds, right? But what if I told you that 90% of the requests occurred during that period where the 5-minute P99 was 300 microseconds? And that's actually a fairly common thing. You're getting a lot more requests, your service is going to slow down. Does that change your answer about, your guess? The missing component from this graph, which you don't see with percentiles, is request volumes. So this is a graph of two different distribution of two different requests from web servers to web servers, along with the corresponding P95s. This is over a constant time period. And the distribution of requests is shown on the y-axis and the sample value shown on the x-axis. So you can see that the blue web server had a lot more samples at lower latencies, and the red web server had a flatter distribution of latencies that were generally higher than the blue web server. So we could say, the red server was slower than the blue server. So what happens if we calculate our 95th percentile by averaging them versus calculating it by aggregating the samples? So if we combine the samples and calculate the correct P95 from the source data, we get a 230 millisecond P95. But if I take the P95 from both sample sets and average those, we get 430 milliseconds. And that's about a 200% difference, which is fairly significant. Now, if these sample distributions matched up, roughly the same, we could average those P95s and get the same answer as taking the aggregate of the samples and calculating the P95 from that. But that rarely happens with today's distributed systems, and it especially doesn't happen when workloads are asymmetric. But as I mentioned previously, if both of these workloads lined up perfectly, we could average there, but you're not going to, when everything's fine, that approach works. But it's when things get out of whack and you need to be aware that your systems are not performing, that you're not able to glean those insights from this approach. So how do people end up averaging percentiles? There's some common workflows that make it easy. One way is to collect latency data without instrumenting your application using a log parser like Google's MTail, which pulls the latency metrics from the logs and then stores it in a time series database or sends it over to a StatsD server or some other aggregation point. But the question is, what latency metric do you end up storing from that? Almost none of the open source tooling exposes the raw samples. They give you the average, the median, or any of the other common percentiles captured for analysis. So if you run MTail on each of your web servers and you store the latency percentiles for each node, you'll get a graph like we just saw. And this is an easy situation to avoid if you have this knowledge, but that's usually the exception as opposed to the rule. Though I've talked to folks who do this and they say, yeah, we know it's not correct some of the time, but this is the best we have right now, and we don't have time to change it, which is a reality also. So let's take a look at how we can calculate service level objectives the right way, and we'll look at three approaches, the third being histograms. So as I mentioned a couple slides ago, we can do this with log data, and we can essentially pull out the latency of each request from log data, and we can store the raw sample somewhere on disk. But the problem with that is it gets very expensive to do that. You're talking about a gigabyte of data for 10 million requests, and that's for one host. If you're collecting API data, you may need to multiply this number by, several dozen servers or so forth. And an additional concern there is if you're serving web pages, you might just want the latency of one page, the HTML itself, not the images. So, now you're collecting, 10 to 100 times as much data on top of that. And, we can take those logs and throw that data into HDFS or Elasticsearch, or we could just run a distributed grep count on there and query out the log files. And that's pretty straightforward, but you do need lots of servers to handle this, and it's a fairly expensive approach. So this is not an ideal approach, but the methodology for that is basically you pull all the latency samples out for a time window, you sort them by value, and then you find the sample that is 5% from the largest sample, and that's your P95. It's very easy to calculate P95s this way. It's just the cost effectiveness of this approach is a bit questionable. So once you have your SLI calculated with this approach, you could just as easily generate an SLO from that. For this approach, you could take your 1 year samples, cut it up into 1,000 slices, and for each of those slices, calculate the SLI. Was my P95 met for those 999 slices? And I met my SLO. Again, a fairly straightforward mathematical computation that really probably most people here can implement. So a quick review. It's easy to configure your logs to capture latency. It's easy to roll your own processing code to do this, and there's some open source options out there, and there's accurate results. The cons are it's expensive. See some of the common log vendor pricing out there. Sampling is possible, but it skews the accuracy. It's slow and it's difficult to scale. So we're going to take a look at another approach here, which is counting requests, and folks may have done this approach also. So how do you calculate SLOs by counting requests? Well, you basically instrument your application to count the total number of requests and then the number of requests that violated your SLI threshold. And from that, you can calculate, your percentage of success. And this is very similar to the Prometheus's cumulative LE type histogram, where you specify a number of predetermined bins and count up the number of requests that are under that threshold. So again, you can also do this with some monitoring solutions that are out there. If you instrument your code, you can do this approach with almost any open source or commercial monitoring solution out there. So here's a visualization of this approach. The requests that violated our SLI are in red, and then the total number of requests are in gray. You can generate a graph like this with pretty much GNU plot or Excel or anything out there. And so based on this, we can say our SLO was 90% of requests less than 30 milliseconds. Based on the ratio of requests, we met that SLO. Again, a very mathematically simple approach. The pros of this approach are it's simple to implement, it's performant, it's scalable, and it's accurate. I can keep the two metrics I need in around 128 bytes of RAM, which is basically 164-bit int. And so this, I can scale this as far as I need it, but it's got some cons with it too. The main cons, which are fairly significant, are you have a fixed SLO threshold. If you want to look at a different set of service level objectives thresholds, you have to reconfigure your app and collect data again, which also means that you cannot do historical analysis of data based on different SLO thresholds. And so while this might be an appealing approach on the surface, there are a lot of hidden costs with it. Oh, pardon me, a lot of hidden costs with it, and it's really not an ideal approach. So now let's get to the fun stuff, histograms. I love to talk about histograms. So this is a histogram. It's basically a bar graph, and it's got the number of data samples on the y-axis, and in this case, our latency value on the x-axis. We can use some numbers to characterize particular histograms. The median, 90th percentile, which is also can be represented as Q.9, the maximum, which is Q1. Q is just another notation for percentile, where you use a value between 0 and 1 instead of 0 to 100%. 100%. And the mode of a histogram is the value at which there are a local maximum of samples. So here the mode is the lowest value in there. There's a guy named Gilteen who has an excellent site explaining histograms, which is hdrhistogram.org. I encourage folks to check that out. And so there's a few different histogram types. There's linear, approximate, fixed bin, cumulative, and log linear. But these really represent different attributes of certain histogram implementations. And so you can combine these to create a histogram that fits your business needs. For example, you could create a cumulative log linear histogram, which has bins and powers of tens, but each subsequent bin would contain the sum of the bins with the lower values. And for example, the HDR histogram I referenced is a log linear histogram. I won't go into detail about all these, but I've got some other presentations I can reference here that go into excruciating detail. So here's an example of our log linear histogram that we developed in open source at Circonus. The bin sizes increase by a factor of 10 every power of 10, and there are 90 bins between each power of 10. This particular one, the x-axis scale is in microseconds, and the y-axis is in number of samples. So as an example, there are 90 bins between 100,000 and 1 million, each with a size of 10,000. And this sample histogram shows latency distribution from a load balancer of a web service. And I've overlaid the average, median, and 90th percentile values. And note how the bin size increases from 10,000 to 100,000 at the 1 millionth value. This increase in bin size allows us to cover a wide range of values, but still be able to do statistically correct operations with a high degree of precision on all the data. This existing histogram here represents about 50 million or so data samples, so it's relatively cheap to store data in this format. And the number of data samples is invariant to the size needed to store it. So in this case, we maybe have a couple hundred bins that we store, 50 million data samples. We could store 500 million in that same number of bins, and it's got the same memory footprint, which is a really nice thing about histograms. Histograms also have the property of mergeability, which means they can be merged together as long as they have a common set of bin boundaries. So if I have two histograms, each representing latency distributions, I can merge them together as one histogram. And I can also do that for 10,000 histograms. It's a very mathematically efficient structure. So how do we compute SLOs with histograms? Say if I have a histogram like you just saw, and I want to ask how many requests are faster than 330 milliseconds. Well, the math is pretty simple. I walk the bins from lowest value to highest until I reach the bin that has a value of 330 milliseconds, and I aggregate the bin counts along the way. The sum of those samples is how many requests were faster than 330 milliseconds. It's pretty simple. So I gave a lightning talk of this New Ops days at Splunk, and a well-known SRE from Google, Liz Fong-Jones, read them and brought up the good point. What happens if a value that you're interested in falls between a histogram bin boundaries? So you don't need to be only interested in sample values that lie on bin boundaries. If I'd chosen 300 milliseconds and my bin boundaries are 300 and 400 milliseconds, I can interpolate across those bin boundaries to get an approximate answer. Errors in operational data using the log linear histogram I've shown tend to be about a maximum of 5% errors. And that's really in isolated cases where you have a small number of samples concentrated in one bin, which we almost never see. For example, if I have a bin boundary at 10 and a bin boundary at 11, and I have a data sample at a value of like 10.95, that's going to be approximated to 10.5. So the error there is about 0.45, which is around 5%. So it's got very good precision and accuracy characteristics. So where are the bin boundaries with the log linear histogram I've shown? We have them at 320, 330, and 340, and 10, 11, 12, and also 1 millionth, 11 millionths, and 12 millionths. So basically, we have a range going from 1 times 10 to the negative 128th to 1 times 10 to the positive 128th. So that gives us, an extremely wide range that allows us to represent wide ranges of operational telemetry data. Pros of computing SLOs with histograms: they're very space efficient, far more efficient than logs. Thresholds can be chosen and analyzed as needed. You can apply statistical methods like interquartile ranges, that's IQR, count below, standard deviation. They're mergeable. They're very high performance. The log linear histogram I showed, it's about 1 nanosecond to insert that on, a commodity machine. It's microsecond percentile calculations. The errors are bounded to about half the bin size, and there's several open source libraries available out there. Some of the cons: the math is more complex than other methods, and there's some loss of accuracy in worst case situations. Here's some references to our existing log linear histograms. I'm going to show briefly how you can use these to calculate SLOs just with all this open source software. So if you go ahead and install these libraries, you can write some Python code that looks like this, which is basically creating a Circonus LO-hist structure, inserting some data, and then you can print the count, the sum, the quantile, and it's very easy to manipulate this data. You can also do something more complex like create one, add the latency data, maybe something similar to what I showed you guys earlier with a blue and red web server, and plot it. And that's actually what I did to generate those plots. I used that code that I just showed you. So it's fairly simple stuff here. Most people out here are probably familiar with Python or know someone who is. So in conclusion, averaging percentiles is tempting but misleading. You can use counters or histograms to calculate SLOs correctly, but histograms give you the most flexibility in choosing the latency thresholds. Only a few libraries implement them right now. libcirc LO-hist is one we have out there in Go and C. HDR histogram I mentioned is out there in Java. There's full support for sparsely encoded histograms in one time series database, IronDB, that Circonus produces. We haven't seen support for histograms in other time series databases yet, but the open source code is out there if folks want to go ahead and take that on. And so go ahead and tweet me. Feel free to tweet me with questions on this. I have more talks about histograms on SlideShare here. If folks want to go read about those, I go into some excruciating detail on some of them. So I guess I can take some questions now.
Okay, yeah, so this is Richard again. So we got a couple questions. So the first one is, are you concerned about the loss of precision when using histograms to aggregate measurement data?
So as I mentioned before, worst case scenario, if you, I'll take a case where I'm using a histogram for one sample, which is totally unrealistic, and the bin boundaries are 10 and 11, and my sample is, 10.999. That's going to show up as 10.5 when I calculate my percentile or my average from that histogram bin boundary. So that's going to give me about a 5% error in a totally unrealistic situation. When I have thousands of data points, distributed across several bins, that error really drops to close to zero for real world usage. So I'm not too concerned about that, no.
Okay, now let's try to squeeze one more in. Okay, so suppose I already have aggregates using descriptive statistics, things like average, median, 90th percentile. So can I easily convert those descriptive statistics to a histogram, and then vice versa?
So you can generate percentiles and quantiles, average, median, and 90th percentile from histograms, kind of using the math that I just showed. But you can't really take a percentile and transform it back into histogram. Percentile generated from a histogram as an output. It doesn't contain the sample data needed to transform itself back to a histogram.
Okay, and I'm looking at the clock, and so I just want to say thank you, Fred Moyer. This was kind of interesting stuff.
Thanks, Richard.
Okay, so I'm sitting here changing the presenter. So our next presenter is going to be Colette Downey from Caringo, and she's going to talk about object storage and performance tuning. Now, Colette has expertise that spans the breadth of software development, starting with identifying the requirements, then leading the development effort, and finally, and probably most important, educating the users. And again, submit your questions in the chat window, and if you join our meetup, then we will notify you via the meetup of when we post the materials from this webinar. So I'm going to change presenter to Colette Downey. So she's now the presenter, and she is now speaking. So Colette, you with us?
I am here. And thank you. Are you seeing the webinar thing in there? Let me see.
Yes, we are, with your picture in the lower left.
Yeah, how do I get that out of there? Shoot. I thought it was going to hide behind.
Hey, things look okay.
Oh, you don't see that webinar little doohickey console thing?
No.
Oh, okay,
So
good.
your
It
screen
shows on my
screen.
It's my screen only. Okay. All right. Well, thank you, Richard and Amy, for inviting me to present. Prior to working at Caringo, I worked with Richard and Amy at SES High Performance, where, among other things, I created and maintained simulation models of components using capacity planning tools. I love performance modeling and the hands-on testing, where it was fun to understand the weaknesses in a design and then design a test to break it. But probably none of these match my love for dogs and ice hockey, playing ice hockey, that is. So this would not be a talk about storage usage without an exponentially increasing growth curve. And in fact, the customer whose results will be presented later had this growth rate at their own site. It's clear that with these challenges, you just can't keep doing things the way you used to. So how have companies been handling this? 7 or 8 years ago, over 50% of storage usage was deployed in the traditional SAN NAS manner, but that trend has been decreasing, as shown by the red line. Meanwhile, virtualized server and cloud environment deployments have been increasing. The yellow stars indicate where other deployments have either met or were projected to meet and surpass the traditional environment. It's actually quite remarkable how quickly deployment types are changing. This presentation's feature customer has also turned from the traditional environment to private cloud. Cloud environments are based upon object storage technology. So what is object storage? Block and file are the types of storage that we are all very familiar with. File builds upon block. And while one could argue that object does too, some implementations take a high level of control over block rights and placement. For instance, Caringo's implementation lays down the complete object block sequentially on disk. Block and file are accessible through kernel system calls. Object storage access is handled by applications using HTTP protocol. There are APIs that have been developed around object storage access. The de facto standard right now is Amazon's S3 API, and just about all vendors with private and public clouds support this API. Both block and file have a set of fixed attributes that describe the data, with the file having a little bit more high-level description with file type, or even encoding information about the data in the file name or even the path name. Objects are not limited in their attribute set. In Caringo Swarm, objects have customizable metadata stored with the object, so the user's ability to describe the object data is unlimited. For example, if the object is a picture of a car, its make, model, color, the license plate number, and mileage can all be metadata assigned to that object. What you can do with this metadata is conduct searches amongst objects to form a collection of objects that all contain, well, for example, pictures of cherry red Corvettes, and then operate on that set of data. Sure, you can always create a new set of attribute-like data and somehow map it to your storage that's in block or file, but what an administrative and maintenance headache. With object, it's first class and it's built in. Block and file are best used for fast-changing data where some sort of locking is required. Databases' atomic transactional operations are best handled by block storage. Files, requiring a lot of rewrite collaboration, is best handled by file. Object storage works on an eventual consistency model. Changes to the data are quickly made available to all. However, there is a minimum time granularity, such as a second, and that's due to the nature of how object storage is implemented. So write once or infrequently and read many type workload scenarios are excellent for object store. Block storage is highly performant, so is file, but the scope of these is restricted to a single site. Object storage, which can also be on-prem single site, is also capable of scaling across multiple sites and campuses. For example, you could have two clusters mirroring or set up in a master-slave scenario and have your front-end applications access the data transparently from either. Some examples of where object storage is used today is in photo storage, such as real estate listings, digital videos and broadcasts that are streamed for viewing, and medical images. Well, this is my favorite chart. We are comparing the different storage technologies against qualities like cost, performance, accessibility, durability, and so on. Starting from the left, SAN or block-based storage is the most expensive to set and maintain. And as you move to the right in the chart, the cost decreases and the total capacity that you can support increases. So in this comparison, nothing beats tape. However, when you consider performance, SAN and NAS outshines the others, but you're going to pay for it. Retrieval off tape could take longer than minutes, depending on the media and tape storage technology. For instance, if you have to dispatch some guy to the basement to pick up the right tape, it could take forever. Object storage has decent performance, especially when it comes to aggregate bandwidth. And you will see later results from benchmarking that had required the object performance to equal the file system-based performance at this particular customer. Something else worth noting is that for some complex data types, object storage is a more efficient way to store the data. For example, HTF5 data contains a manifest at the beginning that describes the data contained within and where in the file it is located. With an object store, each piece of unique data can be stored separately as an object, and the description is handled through metadata. So data is accessed directly versus reading from the top and jumping around within a single file. This is a much more efficient way to get to the data that you want. Access to data was compared in the previous slide, the operating system calls that are fast, easy, and direct. However, when you think about authorization, having to support thousands of users with file system credentials, it's quite the burden on the IT administrator. With object storage, tenants and domains are defined, and the stakeholders in the data contained within those domains can be in charge of granting access keys to users who need the access. This offloading the centralized tracking of UIDs and GIDs is one of the many benefits the customer featured later had noted. Previously, we discussed the power of metadata and searching that object storage provides through customizable data. Object storage is not just cloud-enabled, that's its core. Other storage technologies require other applications or interfaces. The ability to protect data from failures is equally covered by block, file, and object. Object storage version of RAID is EC or erasure encoded data, where a 5-2 encoding means 5 data in 2 parity segments. However, there is greater flexibility in protection of objects. Object storage lets you set protection levels and replication by object. This means you can control how much space is used in storage per file. You're also not locked into a single EC scheme that's defined by the hardware. Furthermore, you can set your storage to change protection and replication levels to vary over time. This is another example of decentralizing the administration of the data. Stakeholders in the data can set the protection levels that suit them. The time to recover from failed disks when the disks fail can be quite long with RAID systems unless expensive SSDs are employed. And even then, other hardware bottlenecks can come into play. In an object storage cluster, all the nodes in the cluster participate in the recovery of a lost disk. Each node independently determines if it contains a replica or neighboring segment of an object that was once on the failed volume and initiates the creation of a new one to take its place. This parallelized approach improves regeneration as cluster size grows and more nodes can take part. So, putting this fire hose of information together, there are some use cases for which each of these technologies are clear winners. SAN and NAS are the best in the high transaction, editing, and collaboration environments. Object is quickly establishing itself as the winner for distribution and delivery, like your streaming video, and Active Archive, because it can store large archives at a lower cost and easier to maintain than NAS. For Cold Archive, nothing draws less watts than tape sitting in Iron Mountain. But customers are now choosing to use low wattage disks and servers in object storage clusters for this purpose. Here's a use case that was faced with exponentially increasing storage usage growth, had a limited sized team of administrators supporting an almost overwhelming number of users across the globe. STFC is the Science and Technologies Facilities Council in the UK. Their Rutherford Appleton Labs has deployed a super data cluster known as JASMIN. It's funded by research, educational institutions, and private industry. JASMIN has a supercomputers network and storage, but without quite as much compute. JASMIN provides 4 basic services: storage, including disk and tape, batch, hosted, and cloud computing. It holds data for monitoring volcanoes and earthquakes, crop yield analysis, wildlife and insect migratory patterns. Datasets come from various projects and a mix of instruments, including 12 satellites that stream at least 10 terabytes of data daily. Many datasets, both model and observed data, are too big to be easily shipped around. So JASMIN enables scientists to bring their processing to the data. And there is a large community of researchers, universities, and users supporting many experiments, publications around the world. The constantly increasing capacity and resource base necessitated a shift away from traditional POSIX to RESTful object interfaces. Here's the testing environment. It contained an extremely robust set of clients, switches, swarm storage nodes. There was an ample set of clients at our disposal. The network consisted of super low latency, non-blocking switches with 100 gigabit ports. The switches were organized in a elite SPI network so that every endpoint was only 3 network hops away. The 12 Swarm storage node chassis are all identically configured. Swarm is built around pure object storage architecture that is simple, symmetrical, and does not rely on traditional storage technologies such as caching servers, file systems, RAID, or databases. Automatic load balancing request using a patented algorithm allows for all nodes and all drives to be accessed in parallel, removing the need for external hard load balancing and front-side caching, both of which can present significant performance challenges in an HPC environment, where total aggregate throughput is the goal rather than single-stream performance. The high levels of performance achieved resulted from the elimination of network and storage bottlenecks. So as many of you performance testers know, bottlenecks can sometimes creep up where you least expect them. For instance, during the proof of concept testing, we noticed that reads and writes were just not scaling the way we'd expected. After tuning the algorithm that distributed EC segments to better distribute amongst all the nodes, we were still hitting a wall. In the original POC testing environment, the Swarm nodes had a single 50 gigabit NIC in each chassis. And while these chassis are NUMO architecture, so because there's only a single card associated with just one I/O controller, it was discovered that this was the bottleneck hindering increased performance. As a result of this, the production environment chose two 25 gigabit NICs per chassis. Also, since the object storage is running on clusters of servers, the network performance is a crucial component. So before the actual testing commenced, there was a good deal of infrastructure validation testing, such as using iPerf3 with a parallel option to test that inter-switch trunking fairness algorithms were performing as expected. COSBench was chosen by STFC as a tool to use during the POC process when various object storage technologies were being compared. COSBench is the iometer of the object world. It was developed by Intel and is an open source distributed load testing framework that has web-based real-time performance monitoring. It provides a flexible workload definition capability and communicates with object storage via S3 API. But it is very important to know the limitations of your testing tools. Here are the ones that came into play here. It assumes that all endpoints are behind a load balancer, rather than keeping a pool of connections and drawing directly from it. Unfortunately, a single HTTP error will stop an entire workload test. The workaround for this is to break around your testing into phases, such as writes, like the prepare phase, and then the read phase, and then execute each phase independently. This way, if you encounter an error, you only need to retest that phase. The average throughput reported by the tool includes the ramp up and ramp down activity, so it helps to have other bandwidth monitoring tools going, like nload, or to analyze the detailed output from COSBench and eliminate those periods. Unfortunately, there doesn't seem to be much new development work going on for this tool because it is missing some of the more recent S3 API features, such as support for the latest authentication methods, parallel multi-part write, and parallel range reads. Parallel multi-part write is often employed for large uploads, like research data at Argonne National Lab. And range reads are intricate to the way that video media is accessed. The performance requirements were set by the customer. Since their use case is research data that is typically written once, for example, satellite, and read many, many times, read rate had to equal their current file system read performance. They required 40 megabytes per second per hard drive. For our testing environment, this worked out to be 21.5 gigabytes per second. Write rate is not as important. It only had to be 30% of the minimum read rate. 2 gigabyte files were stored with 5.2 erasure encoding. Client threads were spread across 20 client machines. Being able to distribute the erasure coding computation and segments across all the Swarm nodes is critical to high performance. And as you can see here, that as we ramped up the thread count across 20 clients, the performance requirements were easily met at about 125 client threads for reads and 60 for writes. But we demonstrated that this environment could handle a much higher load and clearly exceeded the customer requirements. NFS performance was important because as users transition over from file system-based access to object, they need to be sufficiently supported. The customer was interested in an NFS single instance throughput of very large files, So typical file system testing tools like Downey++ and IOZone were not appropriate for this scenario. Custom scripts were utilized. Copy from a client's RAM disk for write and DD for read. To be sure that clients and SwarmNFS server were not keeping any files in kernel cache, we restarted SwarmNFS and cleared all the kernel caches between tests. The performance requirement was based on single server instance, but we needed to demonstrate scalability. SwarmNFS, which is the front end to the Swarm cluster, was easily able to achieve the results for that customer. And here's a summarization of the results and the requirements that were achieved through this performance effort. If you would like to read the complete white paper, you can get it at the URL shown here. Also, if you want to learn more about the power of metadata, there's a webinar coming up at the end of the month, and here's where you could sign up for that. I've also provided my contact information if you'd like to ask more questions or send cash. Thank you very much. Any questions?
Oh, yes, Colette, we do have a few questions. So the first one here is, what are the key attributes for an application to use object storage?
Well, for that, I think I would need to draw back on the use case model, where we were showing that usually those distribution, the distribution and delivery environments, active archive, distribution and delivery. Again, the customer that we had highlighted today had a read once, a write once, read many type of workload, because he's distributing this data to researchers and others who needed to compute on it. Active archive is also used as well. Media, especially video and broadcasting, these are very prime environments for object storage. And we're seeing a huge increase in interest from these companies.
Okay, so the next question was, how did you, how did you determine the optimal number of nodes to use in your benchmark cluster? And the question here has the number 12. So I guess you used 12 nodes in your benchmark cluster. So
yes.
How did you figure out that it was 12?
Well, we do have a webinar on that at Caringo where John Bell goes through all that. But basically, he starts by looking at what are the storage requirements, how much data how many terabytes and petabytes do you need to store? So that'll tell you about him, and then also the protection level. So from that, you get a feeling for how many disks we need to support in this environment. And then you look at the different chassis that are out there and how dense you can make each, and then you make the trade-offs between the denseness of the chassis and the bandwidth that you're hoping to achieve out of these set of chassis. In the case of this customer, he had a certain amount of data that he had to support and a growth rate he was projecting. Match that with the cost, because it is a research-based environment, and the performance he was trying to match, and we determined that the 12 chassis was the best model to go ahead and fit his needs.
Okay, and then the next one here, it's pointing at page 10. And the question was, could you have pushed your system a little higher? I guess,
well,
because the curves aren't...
Right, they're not quite flat, and we like to see that when we do our performance testing. We want to know we're done. There was more testing that was attempted beyond this many threads. As I mentioned before, there are issues with COSBench, be throwing errors and stop the test. Those were coming into play as more and more clients were used. There were also other monitoring that was going on to determine, are we reaching limitations in the environment, and such that we are pretty much hitting the peak or getting close to where the peak is. So the combination of the testing difficulties from the tool, not being able to support much over the number of threads that are shown here, with indications that, it looks like we're just about getting to the peak, determined that this was a good stopping point. Plus, we had clearly achieved over and above what we wanted to achieve at that point.
Okay, and then the last question I see here is, Are there any industry standard benchmarks for object storage? Like, for example, we have SPEC and we have TPC, industry standards, and we have the Storage Performance Council. So is there anything anything specific for object storage?
From my experience, there doesn't appear to be. It appears that in many sales scenarios that the customer looks at their environment and chooses what they feel is an appropriate representation, and will usually, call in the various vendors and have a performance bake-off. But it seems to be very customer-driven and individual, as opposed to publishing results across many different object storage vendors.
Okay, well, those were the 4 questions that came in. So thank you, Colette.
And thank you.
Okay, so just to wrap this up, thank you for attending today's webinar, and especially thank you to Fred Moore from Circonus and Colette Downey from Caringo. And the special thanks is due to both these guys are new to the CMG community, so we hope to have them back in the future sometime. And the final reminder is, please join our meetup group. It's free, anyone can join. And the benefit is that you will be notified when this presentation material is posted. That's through Meetup. So once again, thank you for joining today's seminar, and have a nice afternoon. Bye now.